An astronomical phenomenon has got space watchers excited with the confirmation that last year saw not one, but two rare events: the death spiral of a neutron star and a black hole, and their merger. Now, what's even more remarkable is that it happened in a time before dinosaurs roamed the Earth. You can tell I'm excited to talk more about this. We're joined from Perth by Fiona Panther from Ausgrav, the ARC Centre of Excellence in Gravitational Wave Discovery. Fiona, this is huge, but I'm sure for most people, they won't really understand why. Tell us, what is it that you discovered?
So this is a very, very exciting discovery. So these are objects, neutron star and black hole binaries bound together, orbiting one another, that have been theorized for a long time. But we've never actually seen one before. So we've never seen one with light. And what happened in January is the LIGO and Virgo interferometers in America and in Italy, they discovered gravitational waves coming from the death spiral of these two objects. So they spiral closer and closer, and then they finally merge together. And we detected not one, but we actually detected two. So they're a bit like buses. Two will come along at once if you wait long enough.
That's incredible. So these are the most dense things in the universe, right? How dense are we talking?
So a teaspoon of a neutron star, for example, just one teaspoon would actually weigh more than all of humanity combined. So that is incredibly dense to start with. But we kind of sort of understand what neutron stars are made of. They're made of neutrons, these particles that make up subatomic matter. On the other hand, black holes, we're not really sure what's inside a black hole. They're so incredibly dense and so incredibly compact that they actually bend space-time to such an extent that light falls towards them, it can't escape. So the density of a black hole is actually kind of so dense that it's almost something physics cannot describe in any way.
Okay, so you can't see these with your eyeballs, right? You've used some pretty tricky physics in the interferometers to figure out how this is done. Tell me about how delicate these measurements have had to be.
So what we're detecting here is it's not light. We're actually detecting the bending and stretching of space-time itself. So that's the kind of fabric that sits through the whole universe that everything else sits on top of. And when gravitational waves pass through, it causes space-time to bend and stretch in 3 dimensions. But those little fluctuations, they're maybe only the fraction of the size of an atom, the smallest things that make up you and me. So this is something which is, it's so incredibly tiny, and we have to use these massive interferometers, these 4-kilometer long kind of telescopes, I guess, in order to amplify this signal into something we can measure.
So lasers, look, any science that uses lasers excites me. But what you're saying is that these gravitational waves, they're stretching my atoms as well, right? And you're somehow managing to figure that out and then figure out when, way back in time for us, but in space, in reality, these events happened.
Yeah, that's exactly right. So what happens in these big instruments, LIGO and Virgo, is you have a special kind of mirror. And that mirror can be thought of as almost being anchored to a point in space-time. And so it moves back and forth. And that's what we're actually detecting.
All right, so this is all very exciting for nerds like you and I. What does this actually mean? What's going to come out of this discovery? What's next?
So this is the kind of discovery where it may not have any immediate implications, but it's extremely exciting. So neutron stars and black holes, they're not things that we can study here on Earth, but they tell us something very, very important about how matter behaves and interacts, especially in these extremely extreme environments where actually the laws of physics as we know them begins to break down. So what this can actually tell us is how does the matter which makes up everything around us, particularly inside the nucleus of an atom, that teeny tiny little part right in the middle of the atom, how does that actually behave? How is that all constructed?
Dr. Fiona Panther, thank you and your team so much for figuring out all of the answers to the universe. I'll let you get straight back to it.
Thank you.